Thank you. Thanks to the organizers for the invitation and the opportunity to speak here. So I'll talk about Sanov-Type theorem for marked sparse random graphs and its applications. So this is essentially a large deviation principle associated with the component empirical measure of marked sparse random graphs. Okay. I will begin with the motivation for studying such large deviation principles. So the motivation comes from Gibbs measures or random graphs or probabilistic graphical models. So I look at a graph Gn on n vertices. So throughout my talk, all graphs are going to be sparse. And I have alphabet set, a finite alphabet set X. So each vertex in the graph Gn is going to get a mark from this finite set X. And I'm given a probability distribution nu, which is a probability measure on this set X. And throughout the talk, a P of something will be the set of probability distributions on that set. And nu n will denote the n-fold product measure on Xn. So to define a probabilistic graphical model, I have to also introduce this notation. So I look at the space of all rooted trees of depth 1, where every vertex has a x-valued vertex mark. Okay, so here is an example. So there is a distinguished vertex called the root, and there are certain neighbors for the root. And every vertex in this tree, depth 1 tree, gets a x-valued vertex mark. So the set of all elements of this form, I denote by T star 1 of X. So T star meaning there is a distinguished vertex, and 1 means it's a depth 1 tree. Okay, and every vertex gets a x-valued vertex mark. Okay, and I'm given a function Hamiltonian, which is a function on T star 1 space. And this Gibbs measure or a probabilistic graphical model is a probability distribution indexed by the vertices of my graph Gn. So to define that, what I do is I go to every vertex. So here is my graph. I go to every vertex in the graph. I look at the first neighborhood rooted at that vertex. So that's going to be an element of my T star 1 space. I apply my Hamiltonian at that element. So xv here denotes the mark of the vertex v, and xnv is the set of marks of its neighbors in the graph Gn. So I apply the Hamiltonian and I sum over all vertices, and then I take the exponent. And I define the probability measure whose density with respect to the product measure to be proportional to the e to the sum of the Hamiltonians. And the mu Gn is a probabilistic graphical model or a Gibbs measure on this graph Gn. Okay, and to make this a probability distribution, we have a constant, which is a partition function. So in this setup, the partition function is just the expectation with respect to the product measure of e to the sum of Hamiltonians. Okay. Yes, sorry.
I didn't quite understand. Your Hamiltonians defined for rooted trees.
Yes, so Hamiltonian is defined on rooted depth 1 trees, where every vertex carries a vertex mark.
Okay.
Yeah, so,
okay,
so Hamiltonian acts on objects like this and puts out the real world.
Okay, thank you.
Okay, so here is a simple example of a probabilistic graphical model, the famous Ising model. So this is a model to study magnetism. So here the state space is +1 and -1. So every vertex in the graph has a particle which will take either a plus spin or a minus spin. Okay. And the Hamiltonian has this pairwise interaction form. So the Hamiltonian has two terms. One is B times X naught, which is so this capital B is the external field which acts on the root. And the interaction is given by this pairwise term. So where I look at the pairwise product of the root mark with the vertex mark and sum over all neighbors of the root. So this parameter beta in front of this interaction term is the inverse temperature. And if beta is positive, then the Gibbs measure prefers configurations that are aligned in the same direction. And if beta is negative, that's called the anti-ferromagnetic regime. Okay, and there are many other examples from statistical physics and computer science that fall within this framework of probabilistic graphical models. And one of the first questions in such models is to study for suitable sequences of random graphs Gn, look at this quantity called the annealed pressure. That means I look at the average of the partition function where this expectation is with respect to the randomness in the underlying graph. And then I take the log of that and then divide by n and look at the limit of this object. Okay, so we can rewrite this annealed partition function. So recall that the partition function depends on the underlying graph, and it's given by the expectation with respect to the product measure of e to the sum of the Hamiltonians. So I can rewrite this. So when I take the expectation with respect to Gn, I get essentially the expectation with respect to the joint distribution of the graph and the vertex marks, where the graph comes from some suitable random graph family, and the vertex marks are independent and also independent of the underlying graph. Okay, so now if I look at the sum of the Hamiltonians, this is the sum of Hamiltonians, summed over all vertices in the graph. So I can rewrite that sum as a sum over all possible rooted depth one trees, and count how many vertices have a given neighborhood structure. Okay, so I call this Ln the empirical distribution on marked stars, which I'll define precisely in the next slide, which essentially counts a given depth one neighborhood, how many vertices have that neighborhood structure. Okay, and so with this rewriting, I can write the expectation of the partition function as expectation of e to the n times the Hamiltonian integrated against my empirical distribution Ln. And so in order to quantify limits of this quantity, one should understand probabilities of rare events associated with my random variable Ln. Okay, so this is a motivation for studying this type of question. So here is how I define the empirical neighborhood empirical measure. So I have a graph. So what I do is I go to every vertex in the graph and look at the first neighborhood. So if I go to this vertex and look at the first neighborhood, I get this object. So this is a graph with 6 vertices. So this object appears with probability 1/6. And if I go to either this or that vertex, I get 3 neighbors. So that means this happens with probability 1/3. And if I go to the remaining other 2 vertices, I get this. So that happens with probability 1/2. Okay, so this illustration was for unmarked graphs, but I can do the same definition for the case of marked graphs. So in the case of marked graphs, my Ln is going to be a probability measure on my space T star 1, which is a space of all rooted trees of depth 1, where every vertex is marked with a x-valued vertex mark. Okay, and it's a random probability measure because my marks are IID, and also my graph is also random. And to quantify the annealed pressure, we need to understand the large deviations of this object Ln. So if we look at a simpler object, so namely, if I look at only the empirical distribution of just the vertex marks without looking at the tree structure or the graph structure, the asymptotics of that object is well understood. So this is just the usual empirical distribution of n IID random variables with some common distribution nu. So this is a random variable taking values in the space of probability measures on X. So on the one hand, by the weak law of large numbers, this object Ln0 converges to nu, the true law in probability. The large deviations of this Ln0 object is also well known. So this is given by Sanov's theorem. So Sanov's theorem states that the sequence satisfies the large deviation principle on the space of probability measures on X with a certain rate function, which is the usual relative entropy. And the rate function is relative entropy with respect to the true distribution. So the relative entropy is defined as follows. It's the expectation of this Radon-Nikodym derivative of the log of the Radon-Nikodym derivative of nu prime with respect to mu, if nu prime is absolutely continuous with respect to mu and it's infinite otherwise. Okay, and the large deviation principle is essentially roughly a statement that says that the probability that my object Ln0, so it should be Ln0, approximately looks like nu, is of the form e to the minus n times the relative entropy of nu prime with respect to mu. Okay, so that's about the simpler object Ln0. So now, if we look at our object of interest, which is the neighborhood empirical measure Ln, so recall that this is a random variable taking values in the space of probability measures on T star 1. So now, although my graph, the vertex marks of my graph are independent, the random variables involved in the definition of my ln are no longer independent because of the underlying graph structure. So for example, if I look at the red vertex as the root, then the blue vertex is part of the first neighborhood of the red vertex. And similarly, if I look at the blue vertex as the root, then the red is part of the first neighborhood. Therefore, because of this overlaps, the random variables involved in the definition of ln are no longer independent. There is a slight dependency. So the usual Sanov's theorem does not apply. So our first main result is going to be a large deviation principle for this object ln for random graphs with IID vertex marks. And we will focus on the configuration model. So I'll assume that Gn is uniformly distributed on the set of n vertex graphs with a specified degree distribution alpha n, and alpha n converges to alpha. And further, I'll assume that alpha has finite support and will denote the mean of alpha by kappa. Okay, so here is the first main result. So we look at this neighborhood empirical measure. So there is a typical behavior associated with this neighborhood empirical measure. So if I look at the configuration model, then the degree distribution converges to alpha. So we can imagine that this ln, the limiting behavior of ln is as follows. So it converges to some measure eta 1 in probability, where this eta 1 is defined as follows. So I first sample the degree according to my true distribution alpha from my original model. And then I put IID vertex marks on both the root as well as the leaves, according to the true distribution. So this measure is denoted by eta 1, and the typical behavior is that ln converges to eta 1 in probability. Okay, and we show a large deviation principle associated with ln. That means we show that the probabilities that ln is approximately mu is of the form e to the minus n times some function of mu. And so here is our result. So the function has a specific form. It's a sum of two relative entropies. So here in this relative entropies, there are two auxiliary measures, mu check and mu hat, which quantifies the conditional independence as well as independence of the leaf marks of mu. So I'll define mu check and mu hat in the next slide. So the right function has this form. So first of all, it's infinity unless mu is symmetric. So that means, so by mu symmetric, I mean that the law of the edge marginal, that means the law of the root mark and the first neighbor, that pair is exchangeable. And mu must be absolutely continuous with respect to eta 1, which is my true distribution. And the degree distribution of mu should be equal to alpha. Because in the configuration model, you do not have, because a degree distribution is specified, you cannot have a deviation in the degree distribution. So this is an LDP for ln. So actually a more general result holds for the component empirical measure, which I'll talk later. So essentially, instead of looking at the first neighborhood of each vertex, I look at the full connected component rooted in that vertex. And the same result also holds with a similar form, with the exact same rate function for additional IID edge marks. That means in my original graph, instead of in addition to the vertex marks, I can also put independent edge marks. And the same result also holds for more general families of random graphs, such as heterogeneous graphs with vertex types, heterogeneous graphs, and graphs with a fixed, uniform graphs with a fixed number of edges, and so on. Okay, so now I'll define this, this auxiliary measure mu hat and mu check. Okay, so I'm given a probability measure mu, which is a probability measure on my T star 1 space. So what I do is first I look at a size biased version of mu. Essentially, I make the probabilities proportional to the degree of my tree. And now mu check is a auxiliary independent version of mu. So here is how I define mu check. So mu check is so the degree distribution and the root mark comes from my original model. That means the degree distribution is alpha, and the root mark is according to my true distribution mu. And then for the leaves, I put IID vertex marks, where the marginal is the marginal of the first vertex under the size bias measurement. Okay, so this is an auxiliary independent version, which is mu check. Yeah. So mu bar 1 means I have mu bar, which is a size bias version, and then I look at the law, the marginal law of a randomly chosen neighbor of the root, the mark of the law of that. Okay, so this is mu check, which is an auxiliary independent version, and similarly there is an auxiliary independent version mu hat. So here what I do is the root mark and the degree distribution is as before, and for the leaf marks, I look at the conditional law under mu bar of the first leaf conditioned on the root. And I mark the leaves according to this conditional distribution given the root. Okay, so I've explained. Okay, so this is the form of the rate function, and with this definition of mu hat and mu check, the rate function has is an average of two relative entropies. So the first relative entropy quantifies how far is mu from its independent version, and the second relative entropy quantifies how far is mu from its conditionally independent version. Okay, so here are some prior works in this area. So the first one is by in the seminal paper by Bordenave and Caputo. So they introduce a notion of microstate entropy, which is essentially the number of graphs whose neighborhood empirical structure is equal to a given measurement. Okay, and using that microstate entropy, they show a large deviation principle for unmarked configuration model heterogeneous graphs, as well as graphs with a fixed number of edges. And later, this microstate entropy was extended to marked graphs by Delgosha and Anantaram. And then using that extension of the microstate entropy to marked graphs, Baldasso and others, they show the LDP for marked heterogeneous fixed edge as well as configuration model. Okay, so in the rate function in all these works has several combinatorial terms. So here is an example. Here is how a rate function looks like, which has several combinatorial terms and several entropies and relative entropies. So our result, so we do two things. One is we extend the LDP for models with heterogeneous vertex types, for example, random regular bipartite graphs. And the other important contribution is we provide a tractable rate function in terms of relative entropy. Okay, and this type of large deviation principle was also recently used by Bordenave and others in a context of random matrices. Okay, so here is the first application of this result. So it's about this annealed pressure that we talked about earlier. So recall that the expectation of the partition function is given by the expectation of e to the n times the integral of Hamiltonian against the neighborhood empirical measure. So in this expectation here, the graph is according to the configuration model, and the vertex marks are IID from some distribution. Okay, and as a result of our large deviation principle, we can get a variational formula for the annealed pressure. So what we can show is that the annealed pressure is given by this variational formula, where I take the supremum over all measures on T star, the integral of the measure mu with respect to the Hamiltonian minus the rate function J. Okay, and there are also prior works with regards to this annealed pressure on graphs. So there is the Dempo, Montanari, and Sleesun, they show the annealed pressure for factor models for random regular graphs, and our variational problem reduces to their variational problem in that particular setting. So on random regular graphs, there are also other works by Can, who study ferromagnetic easing model, and Kojaglo and others who study antiferromagnetic easing with zero external field. On heterogeneous graphs, there is work by Kantuji for antiferromagnetic Potts model. And in the configuration model, there is work by Can, Remco, and others in the ferromagnetic easing model. Okay, so in our work, we provide a unified result for a broad class of probabilistic graphical models with general Hamiltonians. And I should also mention that our result do not say anything about the quenched pressure, which is the log limit of the partition function for a specific realization of the graph sequence. So for example, there is work by Bayati, Gamanik, and Tetali who show the existence of the quenched pressure for a broad class of model. Okay, so here is how we show this variational formula for the annealed pressure. So the expectation of the partition function is just expectation of e to the n times the Hamiltonian against this ln. And we use Varadhan's lemma to get the variational formula for the annealed pressure. So Varadhan's lemma essentially says that if I have a sequence of random variables that satisfies the large deviation principle, then if I want to evaluate expectations of the form, expectation of e to the n times some f of xn, where f is some bounded continuous function, then this limit is equal to, you look at the largest possible value of f minus I. Okay, so the idea is, if I look at the expectation around a fixed point little x, then the random variable has a contribution e to the n times f of x. And on the other hand, my sequence satisfies the large deviation principle. Therefore, that point x appears roughly with probability e to the minus n times I of x. So the leading term in the expectation is, so the expectation will be given by the leading term, the point x at which this f minus I is the largest. Okay, so in the case of a configuration model with a bounded degree, the map that takes mu to the integral of the Hamiltonian, this is actually bounded and continuous. So a direct application of Varadhan's lemma gives us the variational formula for the annealed pressure. For the other heterogeneous and fixed edge models, this map is not continuous in the usual weak topology. So what we do is we strengthen this topology by requiring that a sequence mu n converges to mu. If it converges in the usual weak topology, and additionally, we also want the average degrees to converge. Okay, so essentially the stronger topology captures the difference between the degree of the two trees. And under this stronger topology, we can show that this map is continuous, and we can also show the exponential tightness of this sequence ln in this stronger topology, and then we can use Varadhan's lemma to get the desired variational form. Okay, so the main point is that the general variational formula for the annealed pressure for a broad class of probabilistic graphical models. Okay, I'll now talk about the more general component empirical measure result. So for this, we have to look at the space of all rooted connected graphs with x valued vertex marks. So I will denote that space by G star of x, and we endo this with the usual local topology. And now I look at this component empirical measure. So I go to every vertex in the graph, and instead of looking at the first neighborhood, I look at the full connected component rooted at that vertex. And I view that as an element of my G star space. And I put a Dirac measure at that connected component, sum over all vertices and divide by n. Okay, so this object un is a P of G star random variable. And note that if I just look at the first marginal of my ln, that means from the root I go one step below. That gives me my empirical distribution, the neighborhood empirical distribution ln.
Get the mu check and mu hat from the Varadhan.
Oh, so that is hidden in the variational formula. Yeah. So in the variational formula, we have the rate function j. The mu check and mu hat is part of this j, and then you have to maximize overall probability measures on T star space. Okay, so this is the object of interest, which is the component empirical measure, which is a random variable taking values in the space of probability measures on G star. And there is the typical behavior of this object un. So in the configuration model, we know that the local weak limit of the configuration model is the unimodular Galton-Watson tree. So this object UN converges in probability to a measure eta, where eta is defined as follows. So first I look at the unimodular Galton-Watson tree with offspring distribution alpha given by my configuration model. And then I put IID vertex marks according to my distribution. Okay, so that eta is going to be my true law. And what our result says is, so we show an LDP for this UN with a tractable rate function as a sum in terms of sums of relative entropies. So the rate function will have this form. So it's a sum over all h. So this h represents the depth of my tree from the root. So the first term in this summation is same as that of the empirical neighborhood empirical measure. And for h more than 1, the term here essentially represents what is the deviation of my h neighborhood conditioned on my deviation in my h minus 1 neighborhood is given by some rho h minus 1. Okay, so now I'll describe the form of this rate function. So to explain that, I have to introduce some preliminaries. So the first one is this property called unimodularity. So this is so we can think of this as a property that generalizes this edge symmetry of the edge marginal in the case of neighborhood empirical measures. So what I do is I look at the root of my component measure UN and look at one neighbor, a randomly chosen neighbor, which I'm calling 1. In the case of neighborhood empirical measures, symmetry just meant that the mark at the first vertex and the mark at the root, this pair is exchangeable. So now in this case, what we have to do is we have to look at the connected component rooted at O, which is represented by this triangle here, and similarly the connected component rooted at 1, which is this here. So if this pair is exchangeable, then we say that it's that measure is unimodular. Okay, so we can write this down in terms of expectations of expectations of functions on doubly rooted graphs. So suppose I take a function f on doubly rooted graphs, and I look at the expectation under the component measure of this quantity. So I sum over all vertices in my graph, and then f applied to G O comma V. Okay, now in the neighborhood, in the component empirical measure, every vertex in my graph appears as root with probability 1 over n. So this expectation is nothing but 1 over n, and then sum over all vertices in my graph, sum over U and V, f applied to Gn U comma V. Okay, but this summation I can also write as the expectation under the component measure, where now I use the root in the third component of f. So this property, so in the left expectation I'm using O comma V, and the right expectation it's V comma O. So this symmetry property is satisfied by this component measure UN. And the symmetry property is what's called unimodularity. So we say that probability measure rho, which is a measure on G star, is said to be unimodular if expectations of functions of doubly rooted graphs has this symmetry property that if I look at the expectation of f of G O V, that's the same as expectation of the sum of f of G V O. So I can switch the role of root and the vertex V. Okay, and what this calculation here shows that for any finite graph, the component empirical measure is unimodular. Okay, so now, so in our rate function, it's a sum of relative entropies, and the hth term in the rate function tells quantifies what is the deviation in the h neighborhood given the h minus 1 neighborhood looks like something. And so in order to specify this deviation, I have to first describe what is the typical behavior of the h plus 1 neighborhood given that the h neighborhood looks like something. And that can be described using this one-step unimodular extension. So what we do is, so we are given a probability measure rho h on depth h trees, and so we start with a depth h tree, and then we extend this one more level and define a depth h probability measure on depth h plus 1 tree. Okay, so to do this extension, what we do is we look at every neighbor of the root, and we extend. So this part here is going to be an h-1 depth tree. We extend each tree below the neighbors of the root using a certain law which I'll describe, and we do that independently across all neighbors of the root. Okay, and this conditional law with which we extend this part of the tree is from row H. So this right picture here shows row H. So to define my extension, I start from row H, which is this part in the right picture without the blue dash part. So this is my row H, and what I do is I go to the first vertex of the root, first neighbor of the root. I look at the blue part, which is the depth h-1 tree below the first vertex. And then similarly, I look at the depth h-1 tree below the root, which is this red part. And then I extend, so given this blue and the red part, I use a certain conditional law to extend the tree below the first neighbor of the root. So that conditional law is in terms of row H. So what I do is I sort of flip the role of the root and the first neighbor. So this left picture shows row H. So I look at the conditional law of this dashed part, conditioned on the part below the first neighbor is the red part, and the part below the root is now the blue part. So I've switched the role of the root and the first vertex, and then look at the conditional law from row H, and then use that conditional law to extend my depth h-1 tree to a depth h tree. Okay, so this is like an extension of the usual definition of the unimodular Galton-Watson tree. Okay, so I do this for each vertex of each neighbor of my root independently. Then I get a tree which we denote by rho star h+1, which is the law of the depth h+1 tree. Okay, so this is a typical behavior that given that my H neighborhood looks like some row H, the typical h+1 neighborhood looks like rho star h+1. Okay, and with this definition, I can now state the full result or the form of the rate function. So first, the sequence UN satisfies the LDP on the space PG star with the following rate function. So first of all, the rate function is infinite unless rho is unimodular and supported on trees, or rho 1, which is the first marginal of rho, is absolutely continuous with respect to eta 1. And we also need that the first neighborhood, the degree distribution of rho must be equal to alpha. Okay, so if all of that is satisfied, then the rate function takes this form. So it's a sum of relative entropies. So this h here represents the distance from the root. The first term, that is h equals 1, is essentially the neighborhood empirical measure. That's the same rate function that I explained earlier. And for h greater than 2, again, I have two auxiliary measures here, rho h check and rho h hat. Rho h check is the same as rho h star, which is the one-step unimodular extension. And the rho h hat is another auxiliary version, which is a conditionally independent version associated with rho h star. So what I do is I look at the last the leaves of rho h star, and then I modify the leaves of the rho h star according to some conditional law given by my rho h. And it can be written down in terms of a product of Radon-Nikodym derivatives. So in this form, it's not clear that this rho h hat is indeed a probability measure, but we can show that rho h hat is a probability measure. Okay, so this is our result. So as I mentioned, the LDP in the configuration model is already proven by the literature that I showed. So our contribution is to show that the rate function takes this form, and also extend the LDP to a broader class of random graphs with heterogeneous vertex types. Okay. So now I will talk about another application of our result. So this is about conditional limit theorems. So the idea is if I look at so given a rare event associated with my neighborhood empirical measure, I want to understand how does the typical neighborhood looks like given that rare event. Okay, and I'll illustrate one such rare event using the setting. So I look at a function h on my state space x, and I define this sum function, which is so f of some marked depth 1 tree is just the sum of h of all the leaves. Okay, and by the typical behavior, we know that if I look at the expectation of this function f under the neighborhood empirical measure, that will converge to the corresponding expectation under the true distribution eta 1. And so here is one question. So suppose I take some constant c, which is bigger than this true value, and then I condition on this rare event that this expectation under the empirical distribution is more than c. So under that rare event, how does this object Ln look like? Okay, so for example, in the case of spin systems, I can take this x to be just 0 and 1, and let's say h to be the identity function. In that case, this expectation with respect to the empirical distribution, this will tell you the average degree of the vertices whose mark is 1. Okay, and we want to understand how does the typical first neighborhood look like when this average degree, when conditioned on this average degree being more than the typical value. So this type of question can be quantified using the Gibbs conditioning principle from large deviations. So what one does is look at a constraint optimization problem, that is where the objective function is the rate function, and the constraints are suggested by the rare event of interest. Okay, so in this case, we have to look at this optimization problem, that is minimize the rate function j over all probability measures mu, whose expectation with respect to this function f is more than c. Okay, and if there is a unique minimizer for this optimization problem, then Gibbs conditioning principle from a large deviation tells us that the conditional limit of Ln is equal to that unique minimizer of this problem. Okay, and using our relative entropy form for the rate function j, we can actually solve this problem completely in this particular setting and describe the unique optimizer mu star. So it turns out that in this setting there is a unique optimizer mu star c, which we can describe as follows. So I have to so to describe this mu star, so first I have to look at the joint distribution of the root mark and the degree. So the joint distribution of the root mark and the degree in my original model is just the product of alpha and nu. Now in the for the minimizer, it takes the following form. So I have to tilt the original distribution with some factor, which is e to the lambda times n times h. So h is my constraint function, and lambda is a constant that is chosen such that the constraint is met. Okay, so in this case, so my constraint is the expected value of this function f under mu. So although this is a function of, although it's written in terms of mu, for this specific choice of f, this expectation is actually just depends on the joint law of the root and the degree. Okay, so once this gamma is given, then I sample my root mark and the degree according to my gamma, and then put IAD vertex marks on the leaves according to some scaled version of gamma. Okay, so this is the structure of my optimizer mu star c in this particular context. And in a recent work, we also show several other conditional limit theorems for more general rare events. And there are also associated phase transitions where when this optimization problem has multiple solutions. Okay, so now I will summarize. So we showed a Sanov-Type theorem for marked sparse random graphs. Specifically, it's a LDP for the component empirical measure of the configuration model where the vertices are marked with IAD random variables, and the rate function has a specific sum of relative entropies form. And using the form of the rate function, we saw two applications. One is that we can quantify the annealed pressure for a broad class of probabilistic graphical models, and we can also show conditional limit theorems given a rare event associated with the marked first neighborhood. Okay, so most of what I've talked about is here on arXiv. Thank you.
Thank you for a beautiful talk. some of these large deviation results, including the ones by Bordenave and Caputo, apply to the configuration model with
Yes.
the degrees
Yes.
and to Erdős-Rényi.
Yes.
It does not have bounded degrees.
Correct.
So
Yeah.
would
So
you be able to do something for the configuration model in the setting where you have unbounded degrees when they decay sufficiently rapidly or something like that?
yeah, we have not been able to do that. So the main in the configuration, the main idea in the proof is first you have to count the number of graphs whose neighborhood looks like some measured row.
Yep.
And in that counting argument, the fact that this degree has finite support is heavily used. So that's why we have not yet been able to show that.
But then you do manage to extend it to the Erdős-Rényi.
Yeah. So in the Erdős-Rényi, so that's a specific case because of this Poisson distribution. So in the case, so Erdős-Rényi is like so you can first look at this fixed edge model. So given that for a fixed number of edges, the uniform graph, so that you can do the same counting argument for that, and then you can get an Erdős-Rényi as a function from there.
Okay.
Yeah, that's what. Yeah.
Wait, so before I have my actual question, when you said the Erdős-Rényi, in which specific regime? Is it like when NP goes to like some positive?
Yeah, all my graphs are sparse. That means
Right,
yeah,
yes, regime, of course. So one thing I was wondering is, what's the motivation for considering these like graphs with random markings? Like, at least for you personally.
So one is like the annealed pressure.
Right.
We saw, one application is the annealed pressure, where you want to compute the annealed partition function. So there, the marks naturally come up.
Right. Oh, okay. Yeah. And like basically, like what I was wondering is like how one would like define an associated like random matrix for a graph with like vertex markings.
Oh, okay.
Of course, for example, for like a graph with like edge markings, there's like a natural way of doing it, but
yeah. So yeah, like I said, all this I presented only the vertex marks case, but all of them extend to edge marks as well. I can put IID edge marks.
Right.
And this work by Bordenave and others, they study some object associated with random matrices. So what they do is they look at they show that there is a continuous mapping from this neighborhood empirical measure to their object of interest, and then they, as a consequence of this, they obtain an NDP for their object of interest. Right. Okay. So there they also look at edge marks. This function H. Oh, okay. So the LDP. Okay, so let me clarify. Okay, so the large deviation principle is for the graph with IID vertex marks. So this is not the large deviation for the Ising model. So in the Ising model, the marks are not independent. So this result does not apply to that. It's only for IID vertex marks. And so the quest. Okay, so how does row head look? So if I take my first neighborhood as a Ising measure. Okay, I'm not sure. I'll talk to you about it. I'm not sure. Yeah, thank you.
One small question. So you one neighborhood of the graph, you're only looking at trees of that point, right?
Yes.
Where in the proof does the tree structure come in? Can't you use a one neighborhood and work with the one neighborhood completely on this?
So so it comes in the counting argument. So when you count the number of graphs whose first neighborhood looks like a tree, you get some formula in terms of some combinatorial quantities. So if you count the number of graphs whose first neighborhood has a cycle, for example, that number is very small. So that doesn't appear in the large deviations. Okay, so in the H neighborhood, so the term, when H equals 1, the first term here represents the deviation in the neighborhood empirical measure. For H more than 1, this term here represents the deviation in my H neighborhood, conditional on my H minus 1 neighborhood is given by something. Exactly, yeah. Because if you look, because the relative entropy of rho with respect to eta, that's going to be infinite. Because if you look at the infinite tree, so yeah, so what we do is we have to take each neighborhood of the root and then do a sum. So this, correct, yeah.
So if there is no more question, let's thank Sarath again.
Thank you.